Hello, everybody. Let's take a deeper look at capacitors, and we're going to model the parallel plate capacitor because it's an easier instrument to understand. So a parallel plate capacitor, basically, or any capacitor, is an electrical instrument that is able to store charges. So basically, if you connect this instrument, which is known as a capacitor from its name, to a power supply, then charges will transfer into the parts of the capacitor, and then it will store these charges and keep them for a very long time, actually, so that when you need them in the future, you can use them again. Parallel plate capacitors exist in many electric and electronic instruments, such as basically your flash in the camera. They exist also in your old TVs, and they still exist in TVs for now on. They also exist in defibrillators, which, when they want to charge the defibrillator to be able to administer or send out a shock electric current into someone's chest if they're having problem with their heart rate, so to revive them, basically. So there is so many actually applications for capacitors, and to understand them, let's look into the parallel plate capacitor. Okay, so this is a parallel plate capacitor. As you can see, you've seen it before. So you can put some charge on the positive in one plate and call it the positive, and you can put the other charge also to the negative. So if you put 3 charges here, just put 3 charges there. And how do you accomplish that? And it's easy. Just you can connect it basically to a battery. Okay, and from now on, I'm going to draw the battery as these 2 things. That's how it's symbolized in an electric circuit. Actually, I drew them wrong because the long one is known to be what? The positive side. So this is the positive side. Sometimes they put an arrow like that. So this is the positive and this is the negative. So once you connect a capacitor to a battery, charges will flow from one side of the battery to the other side, to the one side of the capacitor. Okay, so this will have positive charges on it, and because it has positive charges on it, it will attract the negative charges on the other side. And an electric field, as you can see, is established, and also a voltage difference. So let's say the voltage of this battery is known as V. I have to mention, and you need to be very careful not to connect a capacitor directly to a battery, okay? So this actually whole thing is wrong, okay? Because if you do that, if you connect a capacitor directly to a battery like that, you may cause a fire, because a huge current from the battery will run into the capacitor, and that may cause some problems. So you want to avoid that. We will talk about that later on. You basically have to connect a resistor in between to slow down the current. In any case, so you establish some charges, so charges will flow. Okay, so charges will flow. All right, so we'll have a positive side of the capacitor and a negative side, and that gives rises to an electric field. And because of that, there is also a potential difference. And the potential difference, the charges will keep flying from one side to another until the potential difference between these 2 plates is the same exact potential difference of the battery. So if you increase the potential difference here, if you increase this here, then the voltage difference here will also increase. All right? So that's the rule. You keep charging till the instrument itself has the same potential difference as the power supply or the battery. Okay, so we kind of like established now that the charge on the parallel plate capacitor is kind of like proportional to the voltage difference of the power supply or the battery. So Q is proportional to V. So if I want to change the proportionality into an equal sign, we have to multiply by a constant. I'm going to call this constant C, and V comes down as it is. So basically, the charge on the parallel plate capacitor is equal to V times constant, where V is the voltage. Now this constant here, they wanted to give it a name, so they called it capacitance. Okay, so Q is equal to C times V. C is capital letter and V is also capital letter. Q is mostly going to be used as a lowercase. Okay, so this capacitance is giving you or giving us an idea about how much charge the parallel plate capacitor can store. Okay, so if we want to look into C in terms of the other term and other variables, C is equal to Q over V, and if I want to look into the unit of C is equal to the unit of Q divided by the unit of the voltage. The unit of Q is coulomb and the unit of the voltage is volt, so coulomb per volt is the capacitance. But in honor of, I think, a German, maybe I'm wrong, but I think it's a German scientist or physicist, they called it Farad. So instead of using coulomb per voltage, they use Farad, and they actually make it one letter F for Farad. Okay, so the unit of C of the capacitance is Farad. All right. As a matter of fact, you know, coulomb is a huge unit. It's a huge unit. So if you have 1 coulomb of charge, you basically have like a lot of charges, a lot of electrons. You're carrying a lot of electrons. So coulomb is a huge charge. And voltage is kind of like a moderate size, so like small, you know, like the voltage in your house is 120. But if you have 1 coulomb of charges, that you have a lot of charges, because we usually measure a coulomb charges in microcoulomb or nanocoulomb. So Farad is a big unit. So what we use actually is instead, so the capacitance is measured in microfarad, maybe measured in nanofarad. Sometimes it's so small you can measure it in picofarad. Micro is 10 to minus 6, nano is 10 to minus 9, and pico is 10 to minus 12. All right? Okay. So we also learned in the past that V, which is the voltage across the parallel plate capacitor, is equal to E.d. So let's say the voltage here, the battery is giving us 9 volts, all right? So as a demo example, and the distance between the 2 parallel plate capacitors, I'm going to make up a number, 0.1 centimeters, okay? That's a reasonable number for the distance between 2 parallel plates in a parallel plate capacitor, okay? And now the question is, find the electric field. Find electric field, okay? Created between the parallel plate capacitor, okay? So from this equation, E is equal to V over D. We know that V across the parallel plate capacitor is the same as the battery, which is 9 volts. And now the distance is 0.1 centimeters, which is 0.1 times 10 to minus 2 meters, which is basically 0.001 meter. So 9 volt over 0.001 meter. Or just multiply this by 9,000. So that's what we have. 9,000 Newton per Coulomb, and that's the unit for the electric field. So what if I ask you to find the voltage difference, not between the 2 plates, because we know between the 2 plates it is 9 volts. But what if I ask you to find the voltage difference between 1 plate and midway, which whatever that distance is, but halfway through? Then it would be 9 over 2 divided by 4.5. What if it was 1/3 that way? It would be 9 over 3, because it's a linear relationship between the voltage, the distance, and the electric field. It's all linear relationship. Okay, so now let's go back to this equation here. And we were asked to find, for example, if the charge on this parallel plate capacitor was equal to 1 microcoulomb, 1 times 10 to minus 6 coulomb. And we are asked to find the capacitance. All right? Okay, let's do that. So the capacitance is equal to Q, which is 1 times 10 to minus 6 divided by the voltage, which is 9. So it's 1 over 9 microfarad. So the answer is 1 over 9 microfarad. Okay, this is just a quick demo example. I hope this will set us up to learn more about capacitors later on. Thank you very much and have a good day.